Hello lovelies, in this video we're going to be going through your Edexcel Separate Science Foundation Physics Paper 2, the paper that we've written for 2024. So after each question comes up, I want you to pause, have a go at it yourself on a bit of paper and then play the video and we can work through the answers together.
Light-emitting diodes have many uses. They're used in many electrical devices, including remote controls and traffic lights. Here we're asked to identify the statement that describes a diode. And this really is just going to test that we know what they are, okay? So we should know that a diode is a component which only lets current flow in one direction. So if you didn't know that, stop the video for a minute and make a note of that now. If we look through some of these others here, a component which measures current in a circuit is an ammeter, so not a diode. And a light-dependent resistor is just called a light-dependent resistor, or an LDR. And a temperature-dependent resistor is called a thermistor. However, the diode is a component which only lets current flow in one direction. Now we're asked to circle the correct circuit symbol for a diode. So we should know that a diode is this one. So the circle surrounding it you may or may not see, but what you will always see is that triangle with a line at the end of it, at the end of its point. To run you through these others, just so you know, this first diagram here shows a bulb. This diagram underneath the bulb shows a light-dependent resistor. The fact that we've got this rectangle there shows it's a resistor, and the arrows pointing towards it show it's light-dependent. And this final one here is called a thermistor. So this is what the temperature-dependent resistor looks like. So again, if you're not familiar with each of those and what they are, then stop the video for a minute and make a note on it now. Okay, so now we're asked to complete the flowchart to show the energy transfer that occurs in an LED when it's connected to a circuit with a power supply. So we should know when it's connected to that power supply, it receives electrical energy. And when we turn on that LED, it's a light-emitting diode. And that means that that electrical energy is getting transferred to light energy. So that is the energy transfer that occurs in an LED when it's connected to a circuit with a power supply. Now we're asked to circle the IV graph for a light-emitting diode. Well, this is another memory question. We do need to be able to identify and even sketch these different graphs for a few different components. So remember that a light-emitting diode is just a diode that happens to emit light, okay? It's still a diode. And we know that diodes only let current flow in one direction. Now, this is actually to be seen on these graphs. Because here, can you see that there's no current flowing here? Only in this direction. All of the other ones have current flowing in both directions. It just happens to be negative, which means it's flowing in the other direction. So therefore, even if we didn't have this memorised, but we knew what a diode was, a component which only lets current flow in one direction, we could indeed still identify the IV graph for a light-emitting diode or any diode is this one here. So here we have our big 6-mark question. We're asked to describe an experiment that will find the IV graph of a light-emitting diode. And we can use a circuit diagram in our answer, and I think they're a really useful way to aid our explanation. So let's start off by drawing our circuit diagram. Now, the first thing I'm drawing is the symbol for a light-emitting diode. So what we have here is this triangle with a line against it with 2 arrows pointing away. That's because it's a light-emitting diode. A diode alone wouldn't have those arrows. Then we have that diode connected in series with a power supply and also an ammeter. Then we're going to place a voltmeter in parallel. Now, the reason why we have that ammeter is to measure the current in this experiment. And we always want to have ammeters in series with the component that we're measuring. So then we also have a voltmeter, which is the circle with the V in it. Now, voltmeters always need to go in parallel with the component that we're investigating. And the whole point of a voltmeter is to measure the potential difference or the voltage in the circuit. So there's one last thing that we need to add to this circuit diagram that we're missing at the moment. So we need to have a way to vary the potential difference. And the way that we're going to do that is by adding a variable resistor. A variable resistor looks like a rectangle with a diagonal arrow going through it. So now we've got this circuit diagram set up, and by drawing it and labelling it well, already actually we've got quite a good chunk of these marks in this question. So now let's describe what we're going to do. So once we've set up the apparatus in this way, we're going to record the potential difference and the current. Once we've done that, we're now going to use our variable resistor to change the potential difference. Once we've done that, we're now again going to record the new potential difference in current. Again, we're going to use our voltmeter to measure the potential difference, and we're going to use the ammeter to measure the current. Now we're going to use that keyword that we use in so many of these investigation questions. We're going to repeat this process. Because the more we repeat it for slightly different potential differences, the more data points we'll have for our graph. Now, once we've done this, we'll notice that we're only getting positive potential differences. So we're only really getting half the graph. What we need to do now is reverse the power supply. By reversing the power supply, we're now going to get negative potential differences. And now we're going to repeat the process before of recording the potential difference and the current, and then using the variable resistor to change the potential difference and repeat. So once we've done this now, we're going to have many data points for both positive potential difference and negative potential difference. So now all we need to do is plot a graph of current against potential difference. And this, of course, was the aim of the game. When we go back to the question to reread it to check that we've got everything down, you can see that we were asked to describe an experiment that would find the IV graph of a light-emitting diode. We've done that here. So you see there's a lot of points we can say here. In these 6-mark questions, we don't want to limit ourselves just to saying 6 points. In any other question, that's a fine method, but these 6-mark questions, instead we're being marked slightly differently. We need to make sure that we give as full an answer as possible and not just giving a few points that we'll do at the beginning of the experiment. We make sure that we talk our whole way through from the beginning, the middle and the end of this experiment, and we talk about any apparatus and measurements that we need to take. So there we are. This would be our perfect model answer. This is a very common question, so by all means, get writing this down and get learning this. The electricity produced in power stations in the UK has an alternating current. It's transported from power stations to homes, where it's used in the mains electrical supply via the national grid. However, batteries used in the home provide a direct current. Here we're asked to complete the following sentence. Now let's remind ourselves of what a direct current actually looks like, okay? So if we were to see this on a graph, a direct current will just look like a straight horizontal line. However, an alternating current will look much more like a transverse wave. So it's going up, it's going down, it's going back up again. And so that's what an alternating current would look like. So when we can visualize it like this, it makes more sense. A direct current is a current which flows in only one direction. However, if we were asked, an alternating current is a current which constantly changes direction. And so there we have it. If you didn't know that about a direct current, that it flows in only one direction, make a note of it now. In the UK, the mains electrical supply has a specific frequency and potential difference. Here we need to identify the value of the specific frequency of the UK's main electrical supply. So we simply need to memorise the fact that the frequency is 50 Hz. Next up, we need the value of the potential difference of the UK's main electrical supply. Now this is another one that we just simply need to memorise. There's nothing more to it than that. And it's 230 volts. And so as you can see, I have ticked the 230 volt box. These two facts are really core information and they are such easy marks. So don't pass up 2 marks in your exam by not learning these. If you weren't aware of it, right now stop this video and make some notes on it and make sure that you learn them. Plugs connect devices in the home to the mains electrical supply. Picture shows a plug. Here we're told that the colour of wire A is green, and here we're asked to select the name of wire A. Now looking at this diagram, I can see that that wire is connected right at the top of that plug. So whenever we have a wire plugged into that specific position there, and it's green or green and yellow in colour, we need to know that that is the earth wire. And so I'm going to tick here, earth. Now if we were thinking about the rest as well, just for good revision, we should recognise that the live wire is going to be brown in colour. And the live wire is actually connected here right next to this fuse. So this is going to be a brown live wire. We should also recognise that the neutral wire will be this wire just here, and that is going to be blue in colour, and that is our neutral wire. The fuse is this little part here, and that is for safety. Okay, so if the current gets too high, that fuse will blow. So there we have it. Here we need to select the name of wire A, and the answer to that is the earth wire. Like I mentioned, we know that that is the wire connected right at the top of this plug, and it's also green or green-yellow in colour. Whereas I've given you some bonus extra information here as well. We've got this brown live wire connected right next to the fuse. We've got the blue neutral wire on the other side. And we've got that fuse there as well, which is really important for safety. So there we are. That is what our plug looks like. Plugs connect devices in the home to the mains electrical supply. So here we have a nice diagram of a plug. We're told that plugs are designed to ensure electricity can be used as safely as possible. And here we're asked to name 2 of the features of a plug that is designed to increase their safety. Now there's a lot of things we can say here. We can mention the fact that we have an earth wire. We could mention the fact that we have a fuse, which is just here. We can mention the fact that we have this outer plastic insulation, so that when we touch the plug, we're not touching any of those cables. We can also mention the fact that the wires themselves are colour-coded, so that we can look at them and tell which one is the live wire, tell which one is the earth wire. The final thing we could mention is the fact that we have a cable grip, which is this bit just here, which is going to prevent the wires within the plug from becoming loose. And those are a good 5 different options that we could say that would make sure that we get our marks. Exposed wires are an immediate safety hazard. In the event of an exposed wire, the appliance should not be connected to the main supply until it's repaired. Here we're asked to explain why an exposed wire could cause a person to get an electric shock. So this is a 4-mark question, so they're asking us to be quite specific in the points here. Now I'm going to write down a few options that you can say, 5 different marking points, and any 4 of these would get us our marks. So the first thing that we can say is quite simply, if it becomes damaged in this way, then the live wire may become exposed. and it's the live wire that is the dangerous wire. So if we say something now specific about that live wire, the potential of the live wire is 230 volts. Now the person who might touch this wire and become exposed to this live wire is only going to have a potential of 0 volts. And this is where the danger comes in. Because what we have now is a large potential difference between the live wire and the person. Now, when we have this large potential difference between the live wire and the person, what we can see is a current or a charge pass from the live wire through the person's body. And of course, this is what can lead to that electric shock that the question is telling us about. So you can see this is a 4-mark question explaining why an exposed wire could lead to someone getting an electric shock. And here you can see I've written down 5 different points that would each get us one of those marks. So if you missed one of them, that's fine, you're still going to get full marks. I think this is a really good explanation to learn in case you were to get a 4-mark question asking us about the dangers of exposed wires. The national grid transfers electrical energy from power stations to homes and factories. Transformers are used in the national grid. Here we're asked to write down the correct letter in the box to identify, firstly, a step-up transformer. So to answer this question, we need to recognise that step-up transformers are found before all of the pylons of the national grid. And that's because what they do is they increase the voltage so that when that electricity goes into those pylons, it has a very, very high voltage. And so in this case, the step-up transformer is B. Now next up, step-down transformers, we need to know that we find those after our pylons in the national grid. And the reason for that is that they're taking that really high voltage that we produced and we're making it much safer now so that it's ready to enter our homes. So we always find step-up transformers before those pylons and we find the step-down transformers after them. Now we're asked to explain the importance of step-up and step-down transformers in the national grid. And here we have a 5-mark question. Now there's more to say in this case about step-up transformers, so we want to get 3 good points about step-up transformers. The first thing that we need to recognise is that the job of a step-up transformer is that it increases the potential difference. And so that would be the first thing we say to get our first point. So step-up transformers increase potential difference. So the next thing we can say is that it decreases the current. So far we know step-up transformers increase potential difference and they decrease current. Now the reason why this is important is by decreasing current in all these wires of pylons, we're going to reduce any thermal energy transfer to the surroundings. Now the whole point of this, why this is so important, is it's going to increase the efficiency because more energy is going to make its way through all these pylons to the other side, to our homes and factories, rather than lost to the surroundings as heat energy. So those are 3 things we can say to get our marks. So we still need 2 more marks, okay? So let's think about the step-down transformers. So we need to know that step-down transformers decrease potential difference. And the reason why this is important is it increases safety. Remember that step-down transformers are found just before our homes and our factories. We need our homes to be safe. Voltage is really all about energy, and the higher the voltage we have, the more energy there is. And therefore, if it's too high a voltage, it's much, much more dangerous, much more chance of electrocution and fires. So the whole point of these step-down transformers is they lower this voltage, this potential difference, to a much safer level. And so there you have it. Here are the 5 things you need to say to explain the importance of step up and step down transformers. Now, if you didn't know these facts, I recommend that you make some notes and flashcards on them now and go away and get learning them, because these are really nice, easy marks to get in your exam. Transformers are also used in many other applications, including audio systems. A transformer was used to decrease the potential difference from a 230 volt power supply to the 24 volts required by a low voltage speaker. The current in the speaker is 8 amps. Here we're asked to assume that the transformer has 100% efficiency. However, this first question wants us to explain why actually in real life it's unlikely to have 100% efficiency. And the reason for this is that energy is normally wasted. And that's likely in the form of heat or thermal energy. However, there might be other transfers too. That would be our reason why it's unlikely to have 100% efficiency. Next up, we're asked to calculate the current of the power supply. So the equation that we need to use here for this transformer question is this one here. So the primary potential difference times by the primary current equals to the secondary potential difference times by the secondary current. And so here in this case, we're being asked to find that primary current, the one belonging to the power supply. We know the primary potential difference, and we know everything about the secondary coil as well. So we can substitute these numbers in. We can say that 230 times by this primary current equals to 24 times 8. So if I rearrange this equation by dividing by that 230, I get left with this primary current. And that gives me a primary current equal to 0.835 amps. And that is our answer to this question here. The current of the power supply is 0.835 amps. Now we're asked to calculate the energy transfer to the loudspeaker if it is switched on for 2.5 minutes. And we're asked for the unit as well. So earlier in this question, we know that if we're thinking about that secondary coil connected to that loudspeaker, we know the potential difference was 24 volts and the current was 8 amps. Now in this case, because we know we have 100% efficiency, you could also think about this question by using the primary coil as well and saying that the potential difference is 230 volts and the current is 0.835 amps. And it's the fact that we have that 100% efficiency that means we could use either pair. However, don't mix and match. It has to be both belonging to the primary or the secondary coil. So the equation we need to use here to get the energy transferred is going to be energy transferred equals current times potential difference times by time. And the reason why that's important is because we know time, we know current, and we know potential difference. So here we've got 8 for the current times by 24 for the potential difference, and then we have a time of 2.5 minutes. However, remember in physics, we don't use minutes, we don't use hours, we need seconds in our equations. So we can convert minutes to seconds by multiplying 2.5 by 60, and that gives us 150 seconds. So popping into our calculator, 8 times 24 times by 150, we end up getting, for the energy, 28,800, and the units are joules. And there we have it. Make sure you're familiar with the fact that energy is always measured in joules, so that would always be correct. The watts that they have here, this big W, is what we use to measure power, and the big A is amps, which is what we use to measure current. So make sure you're confident with all of your units, make sure that you're comfortable with how we use these equations, and make sure you know that we need the standard units for things to put them into these formula. The graph below shows the heating curve for water. It shows how the temperature of water changes as the energy absorbed increases. We're asked in this question to write down the value of A, which is the temperature. So to answer this, let's just evaluate this diagram, okay? So you can see that X is found at negative temperatures. And because it's negative temperatures, it means it's very cold. Now that to me tells me that X is actually ice or solid water. Y therefore is going to be liquid water, and Z is going to be gaseous water or steam. So by recognising those different states, we can see that it's when Y changes to a gas, that's the temperature that we're looking for. And we should be familiar with the fact that water boils and changes to gas at 100 degrees C. Here we're asked to explain what the horizontal regions on the graph show us. So I've included this diagram here for us to look at. So here are the horizontal regions we're being asked about. Now notice that those horizontal regions, the temperature is constant. The temperature isn't increasing at all at those points. The reason why the temperature is constant here is because these are the points where we get changes in state. And in these cases, all of the energy being inputted is being used to break the bonds between the particles. So that means that the energy isn't being used to increase the speed of the particles and therefore their temperature. All of the energy is being used to overcome those intermolecular forces. Now, this question here is a 2-mark question. So to be able to get those 2 marks, we need to state 2 key points. I think the most important of all these options is the fact that there are changes in state. We should just understand that of the horizontal regions. But then any explanation as to why the temperature doesn't increase would be your second point. So either you could state that the energy being used to break the bonds between the particles, or we could say that their energy is not being used to increase the temperature. Either of those can get you your second mark. So now we're told that the water is in different states at points X, Y and Z on the graph. So now we're asked to draw a line from each box to show the arrangement of molecules in X, Y and Z. So what we need to do is to recognise what state X is, what state Y is, and what state Z is. Now, because Z is going to be the state that we have when we're at a very high temperature, we can see that this is going to be a gas. X is when the temperature is very cold, it's below 0. And we know that when water is below 0, it freezes. So that means that X is going to be a solid. And Y is the region that we're in when we've come above 0 degrees, we've warmed up, but before we're 100 degrees. And so Y is going to be a liquid. So that's the first thing that we need to do to answer this question. Now we need to recognise that when we're in the solid state, as we are with X, all of the particles have a regular arrangement and they are all next to each other. So this is what we have in X. We can see that they're in layers and they are all very close to each other in this regular arrangement. And that's what we would expect to see with a solid. So now let's have a think about the gas Z. We should know that when we're a gas, the particles are far apart, they're moving with high energy, and they're moving quickly in all directions. And so the one that most fits this, particularly looking at how far apart they are, would be Z going to this middle option here, where the particles are far apart from each other. Now Y now, we can clearly see, is going to have to be the other one, okay? But let's remember that Y is a liquid. The particles are close to each other, but they're not quite as close as they were when they were a solid. And they are moving around each other in a random arrangement. We still don't have that regular arrangement we have when we have a solid. And so Y is going to be this arrangement here. The density of solid water ice is 916.7 kilograms per metre cubed. Calculate the volume of a 2 kilogram block of ice. So this is a calculation question. We need to write down the equation that's relevant. Here we're being asked about density and volume. So that means we're going to use the equation that density is equal to mass over volume. I always like to lay out the information they give me in the question too. So I've written down what the density is and what the mass is so that it's nice and neat and tidy. So now we know density is mass over volume. Now we need to find the volume. Now to do this, we need to rearrange the equation. Now you may be super comfortable with that, but if you're not, remember you can use the triangle. In this case, the triangle has mass on the top and density times volume on the bottom. The way they work is we cover up what we're looking to find, in this case the volume, and look at the triangle to see what the formula will be. So because it's m over d, the volume is equal to mass over density. So that's equal to 2 over 916.7. So there we are now, we've got our calculation. We just need to put that into the calculator, and that gives me 2.18 times 10 to the minus 3. Or you could give it a 0.00218. There you are, that is question D. Here we're told that the specific heat capacity of water in state X, Y and Z is given in the table below. We're told that the specific latent heat of fusion for water is 334,000 joules per kilogram, and the specific latent heat of vaporization is 2,260,000 joules per kilogram. Here we're asked to complete the sentences to describe the difference between specific latent heat and specific heat capacity, and we're told we can use the words from the box to help us. Okay, so these are a pair of definitions that we really need to learn. And so if, when I tell you these definitions, you don't actually have them memorised, then this is the perfect model answer to put on some flashcards and just go away and get learning it. Okay, so let's look at this. Specific latent heat is the energy required to change the something of 1 kilogram of a substance. So latent heat is all about changing state. So that could be between going from solid to liquid or liquid to gas. But latent heat is always about changing the state. So that is our answer here. Then we're told that specific heat capacity is the energy required to the something of 1 kilogram of a substance by 1 degree C. And so this is going to be increase the temperature of 1 kilogram of a substance by 1 degree C. So if you're not already familiar with that definition, then this is your opportunity to make some notes on it and then get it when it comes up in your exam. The beaker was filled with 0.2 kilograms of 25 degree liquid water and placed over a Bunsen burner. The temperature of the water in the beaker increased to 100 degrees C. Here we're asked to calculate the total energy required to increase the temperature of the water in the beaker from 25 degrees C to 100 degrees C. And we're asked to give our answer in kilojoules. So, in order to answer this question, we need to use the equation that states that energy transferred is equal to the mass times by the specific heat capacity times by the change in temperature. And so in order to answer this then, we need to identify what is that change in temperature, what is the mass, and what is the specific heat capacity. Well, first things first here, we can see that the mass is 0.2 kilograms. Now for the specific heat capacity, we need to remind ourselves of the table on the previous page. Now here we're talking about liquid water, which we decided was what Y is. And so we have a specific heat capacity, 4,186. Now we need that change in temperature. So because it went from 25 to 100, the change in temperature is 100 minus 25. So if we put everything now into our equation, energy equals 0.2 times 4,186, and then times by that change in temperature, which is 75. Now, popping that into the calculator now, I get 62,790 joules. However, this question is asking for the answer in kilojoules, isn't it? So we need to know that we can convert from joules to kilojoules simply by dividing through by 1000. And so that's exactly what we do here. And we get 62.79 kilojoules. An investigation was carried out to find how the number of turns on a coil affects the strength of an electromagnet. A wire was wrapped around a large iron nail, and the wire was connected to a battery, as you can see in this diagram. This formed an electromagnet. The number of paper clips that the electromagnet would pick up was recorded, and the number of turns around the iron nail was increased, and the method repeated. A simplified diagram of the electromagnet is shown below. Here we're asked to draw the magnetic field pattern around the electromagnet. So here is the diagram that you need to draw. Now the key features that we need to include in this question. One of them is that the magnetic field lines have to point from north to south, and that's always the case. We should also know that the magnetic field lines are never going to cross each other. That will never happen. And it's also worthwhile knowing that the closer together the lines, the stronger the magnetic field. So as it's like leaving the ends of this electromagnet, you can see that the lines are closer together, and that's where the magnetic field will be stronger. So this is the general shape that you need to know. The magnetic field pattern around an electromagnet is exactly the same around a bar magnet. So if you learn it once, you know it both times. So next up, we're asked to explain why the field inside the electromagnet is strong. So if you look at our diagram, you can see that there's lots and lots and lots of these coils. And when we're inside the electromagnet, the reason why we have such a strong magnetic field is because all of the little magnetic fields from each coil end up adding together to make this very strong magnetic field inside this electromagnet. The results were plotted on a graph. Here we're asked to draw a line of best fit. So to do this, we need to get our ruler out and a pencil, and we need to line up our ruler across the dots so that roughly the same amount of spots are above our ruler as below it. Now this will never be perfect. I won't be able to do it perfect, and you won't be able to do it perfect unless we were computers, but we'll do it our best and use a pencil to draw a line of best fit. If you decide it's a really bad one, you can always just rub it out and start again. But here we have our line of best fit. So now we want to predict how many turns on the coil would be required to pick up 5 paper clips. So to do this, we want to go to our line of best fit, and I can see 5 is here on the y-axis. And I'm going to use my ruler to draw a horizontal line across from 5 all the way up to the line that I have drawn. And then I will draw a vertical line leading downwards. Now make sure that you use a ruler here, because that is going to be important to make sure that you get a nice straight line and our answer is as close to what we need as possible. So this one here was a multiple choice. We've got some options. So 102, nope, it's clearly not that. I can see it looks somewhere slightly below 130. So 126 is the next option, and that does appear to be correct. Next up, 98, nope, 109, nope. So I definitely think 126 looks like our answer here. So now we're asked to complete the sentences to explain the relationship observed between the number of turns on the coil and the number of paper clips it can pick up. We're asked to circle the correct words. So we need to know that when we have more coils, we induce a stronger magnetic field, and therefore we're going to have stronger force of attraction. That should just be a little set of facts that we're really familiar with, and that if you don't know this yet, make sure you make a little note of it now and you get learning it. So next up, we're asked to suggest a limitation of this experiment and give an improvement. So if you have a think about what we've been doing here, we've been looking at picking up 1 paperclip at a time. Now, because it's just 1 paperclip at a time, we're being limited to the size of these paperclips. What about if we could have picked up actually 4.5 paperclips or 2/10 paper clips? We don't know, do we? And so what we need to do is use smaller paper clips to improve this experiment. Next up, we're asked to suggest how the reliability of the experiment could be improved. And this is universally true to all of your sciences. If you're asked about reliability at any point, always say that you can do some repeats. That will always be a great answer to any question where we want to improve reliability of an experiment. Next up, we need to suggest an alternative method to increase the number of paper clips that could be picked up without changing the number of turns on the wire. So the thing that we need to do here is increase the current. Those are the factors that will end up affecting it. How strong is that current? And how many turns are there on this coil? So that would be what we need to do to increase the number of paper clips that we can pick up. All charged particles and objects have electric fields around them. Here we're asked to identify the description of an electric field, and this is a little definition that we just need to know. So we should recognise that an electric field is a region where charged particles experience a force. So the answer to this one here is our first box, a region where charges experience a force. The diagram below shows a negative particle. Here we're asked to circle the diagram which represents the electric field around the negative particle. Well, we should know that when we have an electric field, it will go from a positive charge to a negative charge. We should also recognise that it's going to be a radial pattern, so it's going to be arrows either going towards this spherical charge or away from it. It's not going to look like the two options on our right with these circles circling around the charges, so we can cancel these out straight away. And using the fact that electric fields go from positive to negative, we can then positively identify our answer as this one here. And that's due to its general shape and also the fact that those arrows are pointing towards the negative. Here is an electric field diagram between two parallel plates. Here we need to identify how the diagram shows that the field is uniform. So a uniform field is one that is the same everywhere. It's the same strength everywhere. And the reason why I can see that this has a uniform field is the fact that these lines are all evenly spaced. So it's not the fact that they're straight lines, it's not the fact that there are arrows, and it's not the fact that the arrows are pointing from left to right. Uniform fields will have evenly spaced field lines. Electric fields are responsible for the effects of static electricity. Static electricity has many useful applications. Static electricity is used to spray an even coat of paint onto cars. The car is connected to a negative electrode and the paint spray is connected to a positive electrode. Here we're asked to complete the sentences to explain how this ensures the car is evenly sprayed with paint. And we are to use the words in the box to help us. So it starts, paint particles all have, and if you look at the diagram here, you can see it's connected to a positive electrode. As a result, we can say that paint particles all have a positive charge. Now, because they're all going to have a positive charge, and we should know that like charges repel, the paint particles will repel each other. This means the paint particles something and gives an even coat. Well, as they're all repelling each other, they're going to spread out, and that's what gives it that even coat. So now onto the car. The car has and again, we need to look at the diagram here. I can see that the car is connected to a negative electrode here. So I'm going to say that the car has a negative charge. And this is the something charge to the paint. Well, it's the opposite charge to the paint. And that's really important because the fact that the car is the opposite charge to the paint means that it's going to get attracted. So all those paint particles are going to get attracted to the car. and this ensures that the back of the car gets painted. As well as having many useful applications, in certain situations static electricity can be dangerous. Here we need to identify one dangerous situation that can arise from static electricity. So here we recognise that we need a dangerous situation. So although yes, it's true, it can cause our hair to stand on end, that's more of a nuisance than a danger. Certainly not going to poison someone, but it can cause an explosion. Because with static electricity, it can cause a spark. So under certain circumstances, that spark could be enough to cause an explosion. So that is going to be our answer to this one. An investigation was carried out to determine the relationship between the volume and the pressure of a gas. A cylinder with a piston was placed in a water bath. A mass was placed on the piston and the volume of gas calculated. This was repeated with different masses to change the pressure. So we're asked here to explain why a water bath is used. And we need to tick one box only. Now the reason in science why we often use water baths is to keep temperatures constant. So in this particular case, it's to keep the temperature of the gas constant. However, of course, this is something that will apply to all of your sciences and lots of different experiments. So if they ever ask you why we use a water bath, it's always going to be to keep the temperature constant. The results were plotted on a graph, and here we can see a nice curve showing the relationship between volume and pressure. Here we're asked to describe the results shown in the graph, and this is a 3-mark question, which means we need 3 descriptive points about this relationship. And what I like to do is I like to think, first, what is the general trend? So here I can see that as the pressure increases, the volume decreases. Now that is clearly true from this graph. However, for our second point, we can go into a little bit more detail. So if the pressure was just increasing and volume decreasing, there's lots of different patterns that could show. But here, if you look at lower pressures, a little bit of a change in pressure actually has a bigger impact on that volume. We get a bigger decrease in volume than at higher pressures. So for that reason here, we can say that at lower pressures, an increase in the pressure has a bigger effect on the decrease in volume than at higher pressures. And for our final point here, we want to really state that relationship. So here, for our final point, we can say that that pressure is inversely proportional to the volume. So that's a much more mathematical and scientific way of expressing the fact that as one goes up, the other goes down. So that's what we want to state for our third point. The results can be used to derive Boyle's law. Boyle's law states that pressure times volume equals a constant. Boyle's law also tells us that if the volume was changed, the pressure would also change. Here we're asked to complete the sentences to explain why changing the volume of a container of gas would change the pressure. And we've got all these words in the box to help us. So here we've got, as volume decreases, there are going to be more frequent collisions of gas particles with the walls of the container. And so that's what we need to say to complete that blank. As the walls close in and the volume gets smaller, we have more frequent collisions. So next we want to state that each particle exerts a force on the wall of the container when it collides. And there is therefore, as the volume decreases, a greater force on the walls. And that is why, if we were to decrease the volume, we would see an increase in pressure. So if you didn't realise that explanation, then this is a perfect model answer for you to write into your notes and to get learning. When the gas in the cylinder has a volume of 80 centimetres cubed, the pressure is 20 kilopascals. Here we're asked to calculate the pressure in the gas when it has a volume of 150 centimetres cubed. Well, we have learned, and we were also told on the previous page, that pressure times a volume will always equal a constant in a closed system such as this. Now, for that reason, if we compare together the 80 centimetre cube and the pressure of 20 kilopascals, we can times those together to work out what this constant is. So if we do 80 times by that 20, we end up getting 1,600. And that is our constant. And so long as we keep using centimetres cubed in kilopascals, we don't have to worry about units there. And see the answer here wants kilopascals, just like we had for the 20. So that is our constant now. So now we can repeat that same equation, pressure times volume equals constant, but this time we're going to know that the volume for our new situation is 150, and our constant has stayed the same because it's a constant, okay? So we can substitute those values in. We can say that the pressure times by 150 for the volume equals 1,600. So now we just need to rearrange this. If we divide by 150, we find pressure is 1,600 divided by 150. And that gives me a pressure of 10.666 recurring. And so if I round that up, that gives me 10.67 kilopascals, or you could write 10.7 kilopascals. And that is going to be the pressure in the gas when it has a volume of 150 centimetres cubed. The person is using a wheelbarrow as a lever to transport a load of mass of 20 kilograms. The weight of the wheelbarrow is 90 newtons. The person used an effort force of F to lift the wheelbarrow. Here we're asked to calculate the weight X of the load. So we were told that the load has a mass equal to 20 kilograms. We should also recognise that the equation for weight is mass times by gravitational field strength. So as they told us in the question what gravitational field strength is, and we know the mass, we can just plug those numbers into this equation. So therefore we're going to get the weight equals 20 times by 10. And that gives us a weight equal to 200 newtons. So now we need to calculate the size of the moment caused by the weight of the wheelbarrow. So first things first, let's remind ourselves of how we calculate the moment. So we should know that the moment is equal to the force times by the distance normal to the force. And normal means right angles or perpendicular. That's probably what you're more familiar with. Okay, so what we need to do now is remind ourselves of the diagram. So we're looking at the weight of the wheelbarrow, which is the 90 newtons. And the distance from the pivot, which is the wheel, perpendicular to that force, is 0.5 metres. So in this case, the moment will be equal to 90 times by that 0.5, which gives us 45 newton metres, the answer. Now we're asked to identify the direction of the moment caused by the weight of the wheelbarrow. So if we think about the wheel as our pivot, you can see that that downwards force is going to swish it in this clockwise direction. So we're moving in the same direction as the hands on a clock. And so therefore the answer to this one is going to be clockwise. The wheelbarrow is in equilibrium. Here we're asked to complete the sentence to show the principle of moments. And this is just something that we need to know off by heart, so if you don't know it, then just make a note of it now. We should know that the sum of the clockwise moments equals the sum of the anti-clockwise moments, if, as it says above, that wheelbarrow is in equilibrium. So now we're told that the sum of the clockwise moments is 105 newton meters. Here we're asked to calculate the value of the anti-clockwise moment. Well, if we use the information that we just said in part I, we know that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. And therefore, as this system is in equilibrium, as it's told above, we can say that the anti-clockwise moment is 105 newton meters too. So now we're asked to calculate the value of the effort force F required to lift the wheelbarrow. So F is this upwards force here. And around that pivot, you can see it's going to cause an anti-clockwise moment. Well, if you remember, the earlier part of the question stated that this system is in equilibrium, and we said that that means that the clockwise moments are equal to the anti-clockwise moments. Well, we were told earlier that the total of the clockwise moments was 105 Newton meters, and we decided that the anti-clockwise moments would be the same. We also said that we can calculate moments by saying that it's equal to force times by the distance normal to that force. So in this case, as we know that the clockwise moments, and therefore the anti-clockwise moments, totals 105, we can say that that's equal to the force, F, times by that distance to that pivot of 1.2. Now, if we rearrange this equation, we find that F is equal to 105, and then if we divide by the 1.2 to get the F on its own, so remember we're doing the opposite of that multiplication, we find that F is equal to 87.5 newtons, and that is the value of the effort force required to lift the wheelbarrow. So now we're told that the person was offered a different wheelbarrow to lift the load. The new wheelbarrow has longer handles. They were told that it would take less effort to lift the load using this longer handled wheelbarrow. Here we're asked to complete the sentences to describe the effect this would have on the effort force. So we know that the clockwise moment remains the same, and to maintain the anti-clockwise moment, we're asked what's going to happen to the force. Well, we know that if we have longer handles, the distance normal to the force is going to be larger. However, we know the moment is the same. So if the moment's going to be the same and the distance has gone up, then we know that the force has to go down. So as a result of that, the answer to this is that the force will decrease. So it tells us here the clockwise moment remains the same. To maintain the anti-clockwise moment, the force must decrease. And so reminding ourselves of this equation at the top of the page, which states that moment equals force times distance. Remember that force and distance are inversely proportional to each other. And therefore, if the moment stays the same, if one thing happens to, say, the distance, then the opposite will have to happen to the force due to that inverse proportion. But good work, that is this question on moments finished. Decorative garden lights are arranged in a series circuit. Here we're asked to give an advantage of arranging these lights in a series circuit. So we should know that a great thing about series circuits is that you only need to do one switch and everything will turn on at the same time. So that is a definite advantage to these, because otherwise imagine going around your garden or your Christmas tree turning on every light one at a time. Won't be suitable, will it? So that's a great reason why series circuits suit this. So now we need to give a disadvantage of arranging these lights in a series circuit. Now, this is like the flip side of what we just said. The problem is if one light breaks, then you've broken that circuit and none of the other lights will turn on either. So that is our disadvantage. So now we have a battery with a potential difference of 12 volts. It's connected to a series of two lights of equal resistance. The resistance of each light is 24 ohms, and we're asked to calculate the total resistance in this circuit. So we should know that in series, the total resistance is just equal to the sum of the resistances. So in this case, the total resistance will be equal to 24 plus 24. So that gives us a total resistance of 48 ohms. Next up, we have a recall question. We're asked to identify the definition of current. So we just need to know this definition, so if you don't know it, time for a flashcard. The current is known as the rate of flow of charge. So that's a nice easy thing to remember to get some easy marks. So next up, we're asked to calculate the current in the circuit. So to be able to work this out, we need to know which formula to use. At the minute, we know that the voltage is 12 volts, we were told that earlier, and we worked out that the total resistance in this circuit was 48 ohms. So that means that we need an equation with a potential difference in it, with total resistance in it and with current in it. So here we have potential difference equals current times resistance. Or you might know that equation as V equals I times R. Both of them mean the exact same thing. So here we need to get the current though, don't we? So we're going to need to rearrange our equation to get current as the subject. So here we've got current equals potential difference, and then we need to divide by that resistance, doing the opposite of the multiplying, to get the current on its own. So in this case, that gives us 12 over 48, which gives us the current equal to 0.25 amps. The lights were left on for 1 hour. Here we're asked to calculate the amount of energy transferred during that hour. So here we need to know which equation to use again. The equation we're going to need here is that energy transferred equals current times potential difference times time. And the reason why that one is suitable is because we've just worked out the current, we were told earlier the potential difference, and in this question we're told the time. So we've got everything we need to get that energy transferred. So the current we worked out to be 0.25 amps. We were told that the potential difference was equal to 12 volts. And in this question, we're looking at a time of 1 hour. However, remember, in physics, we don't use hours in our equations, we need seconds. So we can convert 1 hour to seconds by timesing it by 60 to get minutes, and then timesing it by 60 again. So that means 1 hour is 3,600 seconds. So here we've got energy transferred equals, and then we're going to have 0.25 for the current, times 12 for the potential difference, times 3,600 for the time. And that gives me 10,800 joules. And that there is the energy transferred during that hour.
Well done for making it to the end of this paper, lovelies. I'm really, really proud of all of your hard work.